winning $1 million with magic squares. Is that even possible? Is that just a clickbait title? Surely that can't be done, can it? Well, I would say maybe. Maybe. Because I have an idea. There's $1 million prize, it's real, and magic squares are real. And the thing is, I can keep following the plan until I get $1 million, or I get a YouTube following. Either way, it works out. The plan can't go wrong. As long as I follow the plan, it's great. It can't go wrong. So what's the plan is this. The Millennium Prize problems are some of the most famous, most amazingly difficult problems in mathematics. There's $1 million prize for the solution to each one. But they're so difficult. What are they? What do they even mean? How could I or you attempt to solve any of them? Well, in this video, I will explain using the magic square what is P versus NP and how it can be solved. Maybe this should be called understanding a Millennium Prize, not winning. If you watch this to the end, you will understand P versus NP. So first of all, what is the magic square? Well, the magic square is a 3x3 grid, which all the columns, rows, and diagonals add up to 15. Now, if you just try this naively, I recommend if you haven't done it, try it now. Hit that pause button. Here it is. I'm just going to put in 9 up here. 9's pretty big, so I'll go with the 1. Now I've got 9 and 1. I will put a 5 in that top right corner. Seems like I've got a free choice now. 5's a middly number. Put it with the 6. Perhaps 6 and 5 is 11. I need the 4. 4 and 9 is 13. I can put the 2 in the middle. That is still free. It's going well. 6 and 2 is 8. I can put the 7. This isn't bad. Oh, 7 and 9. I've gone bust on the left-hand column. That's the magic square game. You can play that game yourself. If you haven't done it, try it. Spoilers. The solution, I'm about to give the solution. And it's amazing. If you have never seen this, get ready for something incredible in mathematics. Okay, the solution is this. Put the 5 in the middle. There are 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 is in the middle of those numbers. We put it in the middle square. Now, so I put the 9 here. 9 and 5 is 14. I need that 1. Where's it gone? There it is. Put the 1 in here. Again, 9 is a big number, so I better put it with something fairly small. Let's put it with the 2. And the 2 and the 4. 2 and 9 is 11, so 4 is 15. And this is where the magic happens. This you saw before, and if you try, you can try for a long time. But from now on, it's basically fixed. 4 and 5 is 9. We put the 6, 15. 6 and 2 is 8. We need a 7. We have a free 7. 15. 7 and 5 is 12. We need a 3. It makes 15. And finally, 4 and 3 is 7. 6 and 1 is 7. We need an 8. We have an 8 free. 15. Check the diagonal. 2, 5, and 8 is 15. 15 always round. It's magic. Could it be magic? How does that work? That is the P versus NP in a nutshell. Why? Well, to understand that, you must know what is P and what is NP, and they stand for polynomial and non-polynomial. So let's have a quick look at that. Okay, so all mathematics is basically made up of 4 functions. Well, 4 types of functions, which is quite surprising. You'd think there'd be more than that. But there's not, there's 4. So for an example, polynomial, exponential, factorial, and trigonometric are the types. So to make it clear, let's put an example of the number 2. So if we have x equals 2, a polynomial is something like a squared. So 2 squared is 4, 2 cubed is 8. 2 to the power of 10 is 1024. So that's a polynomial. An exponential is the other way around. So instead of doing 2 to the power of something, we have something to the power of 2. So 2 to the power of 2 is 4. 3 to the power of 2 is 9. 10 to the power of 2 is 100. Then we have factorial. Factorial is the number multiplied by the next number down, So for 2, it's just 2 multiplied 1. If it was 3, it would be 3 multiplied 2 multiplied 1. In fact, let's quickly check out the results for 3. So for 3, we have 3 squared is 9, 3 cubed is 27, 3 to the 10 is 59,049, then 2 cubed is 8, 3 cubed is 27, and 10 to the 3 is 1,000. And then 3 factorial is 6. So we're not interested at all in the numbers here. We're only to the extent of what grows faster. Polynomial, exponential, or factorial. If we make the x big, which of those is going to grow faster in general? So if we go a bit, 4, 5, 10, 100, a million for the x, what's going to get bigger faster? So if we go to 10, we see x to the 10 is 10 billion, 10 to the x is 10 billion. So polynomial and exponential have reached each other. Factorial is still only 3,628,800, so quite a lot lower. But then if we keep growing and growing the x to 100, we find 100 to the 10 is 100 trillion? 100 trillion trillion. 2 to the 100, and we start getting into we need the notation here. If 2 to the 100 is that big number, 3 to the 100 is 5.15 times 10 to the 47. 10 to the 100 surely is 10 times 10 to the 99. Factorial, 100 factorial. 9.33 times 10 to the 157. That means a number with 158 digits. It's way bigger. So as the x gets bigger, the factorial and the exponential will get way bigger than the polynomial. Whatever you start with, even if the polynomial is bigger, polynomial equation might be bigger to begin with, if you keep growing and growing the x, the exponential equation or the factorial equation, the non-polynomial equation, always gets bigger than the polynomial over time. Why do we care about that for magic squares? How is the P versus NP related to the magic square? That is this quality of check versus solve. Now, we intrinsically know what that means, but let's think about it mathematically. What mathematically does it mean to check something versus what mathematically does it mean to solve something? So mathematically, the time taken to check something isn't a time in seconds, it's the number of operations. It's the number of operations we need to check. So, for example, for this square, to check this row, it's 1 plus 6 plus 8, which is 3 operations. This row is 7 plus 3 plus 9, which is 3 operations, and this row is 5 plus 2 plus 4, which is 3 operations. So they're down 1 plus 7 plus 5, 6 plus 3 plus 2, 8 plus 9 plus 4. Again, it's 9 operations, so it's 3 multiplied by 3, and then the 2 diagonals, 1, 3, 4, 8, 3, 5. So it's 9 plus 9 plus 6, which is 24 operations to check a 3 by 3 magic square. And then in general, if you have n by n, it will be n squared to check one way, n squared to check the other way, and 2n to check the diagonals. So number of operations to check an n by n magic square is 2n squared plus 2n. Okay, so what's slightly harder is the number of operations needed for a solve. So just say we don't know anything. We're just randomly putting the squares in to solve. We could put 9 different squares into the first place. We could put 9, 8, 7, 6, 5, 4, 3, 2, or 1 in there. Once we've done that, there's only 8 selections for the second place. We could put 8 possible ones here. Once we've done that, we could put 7 possible ones in there, and so on. So the number of total combinations is 9 times 8 times 7 times 6 times 5 times 4, which is a factorial. So we see that the number of the time to solve, if we just solve naively and search exhaustively for every solution, is non-polynomial. So we now understand what are operations, and this is basically the whole of computer science. If you have to solve a problem, 1, you've got to get the right answer. But 2, you want to do it in the shortest time, which means the smallest number of operations. And everyday things that computers do, like sorting, the most basic thing, here's some numbers, put them in order. There are known sorts which have a known algorithm which will take polynomial time, whereas if you just put them in random order and hoped, it would be a factorial. So that's an easy problem. There are also harder problems, which are non-polynomial time problems. Nobody knows a solution which will always solve those in polynomial time. One very famous example is called the traveling salesman problem, where you have a map and you have to go around different lengths between points and get back to the start. I like to think of it as the pizza guy problem. If you had a Domino's pizza, you have to get out to different customers and back to the start in the minimum distance. There's no known solution given the map that will always give you the shortest path in polynomial time as an algorithm. So if you understand about counting the number of operations as polynomial or non-polynomial and checking and solving, the $1 million Millennium Prize problem is easy to understand. It just asks if every problem that has a solution that can be checked in polynomial time can be solved in polynomial time. So that's sort of unbelievable that all these difficult problems that nobody has found a polynomial solution to, there is a solution out there, that you just have to be clever enough to think about it the right way. And is there any question in computer science where it's considered to be a non-polynomial question, that we don't have a polynomial time algorithm, but we know for sure that the polynomial time algorithm does exist? It's just that nobody's found it yet. If there's a question like that, and you can look into that question, maybe that will unlock some future answers or other information about P versus NP. Does such a question exist? And the answer is, of course, yes. The magic square. Put the 5 in the middle is a solution that unlocks the 3x3 in polynomial time. And this video is getting too long, but we can see that here. So now we have a question where the solution is available in polynomial time, and it must scale. It must be possible for the 4x4 and the 5x5 and the 6x6. And that is unsolved mathematics currently. Nobody knows how to find all the magic squares for any number bigger than 6. And it's not really discussed. As far as I'm aware, that's the only problem we have. That's the only example where for a small number of n, we do have a polynomial algorithm, and for a bigger, we don't. So it would be an excellent example to study to understand more about P versus NP. And obviously, as you tell a child in school, what's the next step in your investigation? The journey of the mathematician, find a bigger, increase the size, find more examples. The next one is obviously 4. Can I, on this channel, find the algorithm for 4 and continue the steps to all of the magic squares and then to all of the NP problems in general? Let's find out. If you want to see why it's polynomial, click the slow motion button, and I believe there's some other buttons down there you might want to click. It's up to you.